Okay, let's solve this electrostatics problem. We're given a problem. We have three charges, Q1, Q2, and Q3. It says if Q1 is a particle with a deficit of 1 electron and it's fixed in place at the origin, here, we also have Q2, which has an excess of 4 electrons. It's fixed in place at x is equal to 1 meter on the x-axis. What we want to know is if we could place a third particle, Q3, somewhere in the region of Q1 and Q2 such that there'll be no electrostatic force on Q3 due to the charges Q1 and Q2. So we'll look at 4 different positions. We'll look at position A off the x-axis above the 2 charges. We'll look at position B between the 2 charges. We'll look at position C to the right of the charges and position D to the left of the charges. So let's try to solve this problem, and we'll use our 5-step process to do so. We're using our 5-step process. We want to state what are our givens. Our given Q1, we'll label it as our variable. It's a charge. It'll have a unit of coulombs. It says here it has a charge of 1.6 times 10 to the negative 19 coulombs. Well, why does it say that? It says Q1 has a deficit of 1 electron. An electron has a quantum of charge, that's one of our theory, E is 1.6 times 10 to the negative 19 coulomb. Now, electron has a negative charge, a quantum of charge. So if we have a deficit, then we'll end up with a particle Q1 that has a positive charge. Q2 has an excess of 4 electrons, so it'll have 4 elementary charges, but negative. So we'll have negative 6.4 times 10 to the negative 19 coulombs. So we see here Q2 has a magnitude of charge 4 times that of Q1 and is of opposite sign. We're also given the distance between the 2 charges. We're given the position, but we'll relate that to the distance between them. We'll label that R, and R is equal to 1 meter. That we're going to use in our theory of Coulomb's law. Coulomb's law, electrostatic force between 2 particles, equal and opposite. The magnitude of that force is relative to the product of the magnitude of the 2 charges, and it's also proportional to the inverse of the square of the distance between them, our inverse square law. And it uses the electrostatic constant K, which is 8.99 times 10 to the 9th Newton meter squared per coulomb, so we'll label that also as our theory. Now, if we want to try to approach our solution, if we start at position A, we want 0 net force. If we want 0 net force, well, there must be more than one force. So our sum of the forces on Q3, if it's at position A, must be equal to 0. Well, what will be the direction? We need a free body diagram then. The direction of the force on Q3 at position A will be, since Q1 is positive, oh, well, what is Q3? Is it positive or negative? We need our law of charges here. Our law of charges says opposite charges attract, like charges repel. So we can have both an attractive or a repelling force. But we need to know what is the sign of Q3. We're not told what the sign of Q3 is, so we can make an assumption. We'll use our law of charges, and we'll make an assumption if we can assume that Q3 is positive, or we could assume that Q3 is negative. So let's go ahead and assume that Q3 is positive, and we'll draw our force vectors on Q3 at position A. So our force vector due to Q1 will be away from Q1 along this same line. If we drew a line up here, it would go through Q3 at position A and point away from Q1. The length of the vector would represent the magnitude of the force. Since Q1 has 1/4 the magnitude of Q2 and the distances look sort of proportional, we might want to draw these 2 vectors 4 times in length. But A could be anywhere up here. We're drawing our force vector on Q3 due to Q2 towards Q2 along this line of action between them. So when we sum these 2 vectors, the x components are always going to be in the positive direction. The y component will be positive and negative, so the y component could sum, but the x component's never going to sum to 0 here. So we could never get 0 net force on the charges at position A, on Q3 at position A. So let's look at position B. If we jump down here and look at position B, again, using law of charges, Q3 is positive, Q1 is negative, so we are going to have Q1 is positive and Q3 is positive, so we'll have a repelling force. Q3 will be repelled by Q1, it'll be attracted by Q2, and both the forces are going to be in the positive x direction. So again, we're not going to be able to sum to 0. So when we have unlike charges, in between the two charges, there's no position in here where we can get a third particle to sit, be it positive or negative, where we're going to get the sum of the forces to equal 0. It might be possible on the x-axis, but to the right of Q2 or to the left of Q1. So let's look at to the right of Q2 first. If we look at to the right of Q2, well, Q1 is again still going to be repelling Q3, so our away from arrow, and Q2 is still going to be attracting Q3 because they're opposite signs. So we get our towards arrow. So now we have two force vectors in opposite direction. So we have, and they're opposite direction. We have no force in the y direction at all. So we could get the sum of these forces to equal 0. So if we plug in our solution and we take a look here, we plug in our Coulomb's law, we get our sum of the forces. I say it's plus or minus our electrostatic constant times the magnitude of Q3, magnitude of Q1, divided by R1 squared. Well, what's R1? R1 is now the distance between Q1 and Q3, so we'll label it up here on our diagram. Why do I say plus or minus? Well, we'll define plus is in the positive x direction, and since Q3 is positive, we'll let that, this will be, we'll use the positive, not the negative. And Q2, we'll use the negative. And we'll sum those to equal to 0. When we simplify, we see that we don't need to know the magnitude of Q3. If we're setting that equal to 0, that's going to cancel right out. And we're just going to, we can solve then for what looks like it's off the screen. There we go. For R1 divided by R2 is going to be equal to the square root of the magnitude of Q1 divided by Q2, or in this case is going to be equal to 1/2, since Q2 is 4 times Q1. Well, if we look at, for that to be equal to 1/2, our R1 is clearly much bigger than R2 to the right of Q2. So this solution is not going to be possible. But it looks like it might be possible if we look at position D. So let's jump ahead here and look at position D. We see position D, now we have our force vectors. Q1 is repelling Q3, but so it's pointing it to the left now. Q2 is attracting Q3, so it's pulling it to the right. We had them in opposite direction. We solve, we still get R1 over R2 must be equal to 1/2. Well, now, again, R1, distance between Q1 and Q3, that is shorter than R2. So now we can go and we can get a more exact solution. We go in, we plug in. We also know what R is, right? And we see that, well, what is R2? R2 is R1 plus R. So if we add this equation, we can solve that and we get R1 over R1 plus R is equal to 1/2. So our R1 should be equal to R, and our R2 is equal to 2R, and voila, we can put a particle Q3 there, and that particle will have no net force on it. Now, does it matter whether Q3 is positive or negative? It doesn't. If Q3 is negative, just the direction of these arrows swap. So in this case, it doesn't matter. The sign of Q3, the magnitude of Q3 determines the distances, or it doesn't matter the magnitude of Q3.